Today, we're going to dig into a really strange paradox that's popped up right at the heart of AI research. It's a story about a huge experiment that went completely sideways, but in a way that reveals something truly fundamental about how these systems think, and maybe more importantly, how they break.
It sounds like a crazy question, doesn't it? I mean, for years, we've been told that more computing power, more thinking time, always equals a smarter AI. But what if that's just wrong? What if, under the right circumstances, thinking harder actually makes an AI less intelligent?
And this isn't some thought experiment. A recent, pretty major study from DeepMind found something that just blows my mind. When they pushed a model to really refine its answers, a staggering 38% of its answers that were already correct flipped and became wrong. So what in the world is going on here?
So the whole point of the study was pretty simple, right? They wanted to improve the AI's performance. The plan was to have it generate thousands of possible answers before it picked the best one. The idea was that this super deep thinking phase would lead to better, more optimal answers. But instead, it led to total instability and degradation. The model didn't get better, it actually got worse.
And that brings us to what everyone's now calling the 2048 sample paradox. It's this really fascinating mystery that honestly challenges our entire understanding of how AI reasoning works. The actual method is pretty wild when you think about it. So to figure out how tough a question was, the AI would generate 2048 different sample responses. You could think of it like brainstorming, but on a massive industrial scale. But here's the kicker. This process, which was supposed to be a warm-up, was actually what was causing the system to break down. It was like it accumulated so much informational strain that it started to fail before it even got to the final answer.
Now, the thing is, conventional AI theory doesn't really have a good explanation for this. So a totally new framework is proposing a really radical idea. What if we stop looking at AI like a computer and start looking at it like a physical engine? So let's put on a new pair of glasses, the lens of conversational thermodynamics.
This quote from a researcher named Erickson Katz really just gets right to the heart of this new idea. It suggests that keeping things orderly, keeping meaning straight, it all requires energy. It doesn't just come for free with more computation. Every single thought has a cost, and that cost is measured in disorder, or what scientists call entropy.
And this brings us to our first really big idea, semantic entropy. So forget about computer code for a minute. Just imagine each one of those 2048 samples as a tiny little puff of heat, or maybe like mental clutter. On their own, they're nothing, but when you add them all up, they build and build, creating this huge load of informational disorder that the system somehow has to deal with.
And this visual just shows the problem perfectly. As you can see, with every single new sample the AI considers, that semantic entropy in the system just keeps climbing. And it's not a straight line either. The disorder builds up really fast at the beginning, and then it starts to level off as the system gets closer and closer to just total chaos. That line at the bottom, the x-axis, that's basically DeepMind's 2048 sample process in action.
Okay, so what's the direct result of all this rising entropy? Well, it has a name: synaptic drift. The mistakes that DeepMind was seeing weren't just random glitches or bugs in the code. No, they were a predictable, systematic decay of meaning itself. As that informational heat rises, the AI's grasp on what things actually mean literally begins to melt away.
All right, so we've got the mystery, and we've got a new theory. Now for the fun part. Let's put them together and see how this whole thermodynamic view decodes exactly what happened in that DeepMind experiment.
Okay, seriously, this is the smoking gun right here. This map, which comes directly from the conversational thermodynamics model, it predicts the exact point where a system will cross a phase threshold, a tipping point, and enter a region where entropy just takes over and collapse is pretty much inevitable. And would you look at that red dot? DeepMind's 38% failure rate lands perfectly on that predicted collapse curve. That's not a coincidence, that's a confirmation.
This table just lays it all out so clearly. That 38% corruption rate, that's a direct result of synaptic drift. The fact that the model fails on harder problems, well, that's because those problems start with a higher level of informational entropy to begin with, so they're already closer to the tipping point. And the weirdest part of all, that the AI started giving really simple answers just to please the verifiers, that's something called entropy inversion. The model basically creates a simple, low-entropy mask to hide all the high-entropy chaos that's churning underneath.
So what's the really big takeaway here? It's that we've been measuring the cost of AI thinking all wrong. It's not just about the raw number of calculations it can do. There's a hidden cost.
For years now, the whole industry has measured cost in flops, floating point operations per second. It's a simple mechanical count. But the thermodynamic cost, that's the real story. It measures the actual informational load, the strain on the system's ability to stay stable. And the most important part is that while flops increase in a nice, neat, predictable line, the thermodynamic cost of entropy grows non-linearly. It actually accelerates with every single step.
And this chart shows that divergence perfectly. The gold line, that's the computational cost in flops, just rising steadily. But that blue dashed line, that's the true thermodynamic cost, the entropy. You can see it's an exponential curve. It's a hidden burden that grows so much faster than our old metrics would ever suggest. This, right here, is the hidden cost of thinking. So if these systems are constantly generating all this entropy and are always heading towards a total collapse, you have to wonder, how do they even work at all? Well, the answer is a concept called semantic anchoring. It's an external injection of order that works like negative entropy, kind of like a cooling force. And where does this magical, stabilizing energy come from? It comes from us, from humans.
And right here, all the pieces of the puzzle just click into place. You've got the computational cost in gold and that scary rising thermodynamic cost in blue. But look at that green line way at the bottom. That's the anchoring energy, the negative entropy that's being provided by humans. The model shows that without that constant stabilizing input from us, the blue line would always lead to collapse. It wouldn't matter how high the gold line goes.
Now, this isn't just some technical detail for researchers to argue about. This thermodynamic view has some really profound implications for the entire future of artificial intelligence.
So let's just recap the biggest points here. First, AI reasoning has physical limits, just like any engine does. Second, making progress in AI isn't just about throwing more computer power at a problem, it's about managing this informational entropy. Third, and this one is huge, AI cannot stabilize itself. It has to have an external anchor. And that means human oversight isn't just a nice-to-have safety feature, it's a thermodynamic necessity to keep the whole system from melting down.
This quote just drives the whole point home. As we make these AI models bigger and more powerful, we are simultaneously increasing what they can do and the speed at which they can catastrophically fall apart. It's like we're building faster and faster cars, but we're also making the crashes that much more severe.
And all of this leaves us with a really big question to chew on. For years, we've been obsessed with building more and more powerful AI engines, measuring them by how many calculations they can do. But if every single one of those calculations generates informational heat, are we just building engines without a cooling system, basically guaranteeing that they're destined to overheat?